So today we are going to review on the recursion and algorithm analysis. And then this one will be more focused on multiple choice instead of the FRQ, okay? Because in the real exam, I think they seldom test the FRQ for the free response. Okay, so our main topic is the number of function call, number of comparators, number of operators, or a memory requirement. These are something that people always test on, and complexity analysis. And then you need to understand how recursion has been done. And then divide and conquer dynamic programming. These two usually, this one may not test, this one yes. And Euclidean algorithm, yes, sometimes you test it, Fibonacci. Okay, and a few different topics. Okay, so number of the function call. So when you develop an algorithm, number one, you need to solve the problem first. So for developing an algorithm, first you need to solve the problem. So there are many known algorithms that can solve the problem. Okay. But after you know how to solve the problem, you also need to study the algorithm's efficiency. So you need to analyze the time complexity and memory complexity. So you need to study the data structure and also need to study the time complexity, BO notation, NP completeness, and tree, whatever these different structures. So for the complexity analysis, usually the commonly asked questions are the number of recursive call and the result of the recursion. So first one, you need to know about what is the big O notation. Okay, O means omega. It's a Greek word, not an English word. So when you analyze your performance by the time complexity, we write T of n. So T of n maybe is a function of n, okay? And it may be like this, okay? And then there may be a function that is like this, is a lower bound. And there may be a function that is upper bound. So this upper bound, we call it order of n, okay? And lower bound, we call it omega, lower omega of n. Okay, so basically, the big O notation means the upper bound of the function, and it also is just considering the order of n. We only consider the growth rate. Okay, growth rate. So here we have the T of n. You may have different times of steps when your number of n grows. And then you need to consider best cases, worst cases, and average cases. And then when you consider big O notation, you need to ignore the multiplicative constant. So order of n, order of half n, order of 100 n is the same. We all call it order of n. And then the dominating factor will be dropped. So if you have order of 2n squared plus 100n plus 2, we just keep the highest order one. So this one we call it order of n squared. The order n and order constant 1, well, we just drop them. Okay, constant time, we call it order of 1. Okay, roughly that's the idea of the big O notation. Next one, we are going to study the recursion. So recursion, we have the termination condition, recursive formula, and the step-by-step improvement. Okay, these are 3 things you need to remember. That's the basic idea to write a recursive program. So you have sum of n. You started to write if n equals 1, return 1. This one is sum of 1 to n. So this one is the termination condition. And then you write a recursive condition. Okay. And then you actually finish the program and then you call it. Okay. And you can also write with accumulator. So you put an accumulator right here. And you can consider this one as a helper function. So basically, you call termination condition and the recursive relationship. And you can also write a function for original code, okay? Not without the accumulator. So the top one is a helper function, lower one is the original function, okay? Factorial is calculating the n bit. So it actually is 1 times 2 times up to n bit, okay? So when n equals 0, you return 1, okay? And then f of n minus 1 times n equals n bit equals n minus 1 bit times n, okay? So that's the recursive structure. And you can also write a version with the helper function, okay? So these are actually different version. We talk about it when we do recursion already. And then if you convert some function back to iteration, this one is the base condition. And this one is the recursive formula, okay? Now, when you trace your recursive function, you do top down, okay? So you actually calculate Fibonacci of 4, and Fibonacci of 4 is equal to Fibonacci of 3 plus Fibonacci of 2, right? This is called top-down trace. So you can do top-down. However, you can also do bottom-up. So when you do bottom-up, you have f of 2 equal f of 0 equals 0, f of 1 equals 1, f of 2 equals f of 1 plus f of 0, f of 3 equals f of 2 plus f of 1, f of 4 equals to f of 3 plus f of 2. So in this Fibonacci case, actually, bottom up from a smaller number to bigger number is better than the top down, okay? So either way, you can use either way to trace the recursive function. Okay, but you need to know which way would be better. So today's some example, we will teach you how to do it, okay? Okay, so that become this formula, and actually is iterative function. Okay, if you do button up. So look at this problem, okay? This problem. This problem is a problem in the practice exam 2014 practice exam. So there is a recursion of n equals this. What is recursion of 27? So let's see, you have R of 27. You go into here, it's greater than 10. So it becomes recursion of n divided by 3. So it becomes recursion of 9. So recursion of 9, it actually is less than 10. So return n times 2. So this one return 18. So this one become recursion of 18. So recursion of 18 becoming recursion of 6. So recursion of 6 becoming recursion of 12. So this will become recursion of 12. And the recursion of 12 becomes recursion of 4. And recursion of 4 becoming 8. So this one becoming recursion of 8. And then that one become 16. So you got the answer of finally you will return 16. Is that okay? Is that okay? So this one top down is easier. If you want to do bottom up, it's very difficult to do bottom up. Okay, this one, if you want to do bottom up, it's actually very hard to do bottom up. So this one actually top down is easier. Hi, but anyhow, so this one you need to do top down analysis. Okay. Okay, some recursive function may have running index as well. So it actually is the same thing when you do for loop. So for index I equals 0, I less than eta length, you do something. So that I less than eta length becoming your termination condition right here. When you greater than that, you return something. Okay. And your for loop body is right here. Okay, this one is iteration with index. So sometimes recursion with index, sometimes recursion with accumulator, sometimes you have recursion with index and accumulator both. Okay, so there's also a function called recursive palindrome. So basically, recursive palindrome, you have, let's assume that you have a problem that's actually race car. So you check this one and this one the same. So I'm going to do recursive call of this. And then you check these two the same. I'm going to do recursion of this. You check these two, and then I'm going to do recursion of a single E. And then that's actually palindrome. So basically the whole thing is a palindrome. So when you actually go in there, and then you cannot find equal, then you will return false. Okay. Then you will return false. So this is recursive palindrome. Okay. You can also use the low and high if you like. Okay, this is actually, and you can also use a substring to do it. Okay, but here you can also use low and high. Low and high, you do not need to call it a substring. When you don't use the substring, the program would be faster and also save spaces. Okay. And you can also write a version that actually is case insensitive. Okay. So when this one will allow race car to also work. Okay, to also work. Okay, anyway, this part is not important. Okay. Next one, you may have the recursion on 2D grid. So you can traverse a given matrix using recursion. So input is that you want to traverse to every single one. So how can you do that? So you have I and J. Okay, so if I equals this and this equals this, then you are going to print it. Okay. So if you are the last one, you're going to print it. Otherwise, you print this one, and then if J less than, the J is not the last one, so you keep going for bigger J first. Okay, you're going for bigger J first until it is greater than that. Then you will, so if it's greater than the n minus 1, then you use a bigger I and restart from 0. Okay? Is that okay? Then you will start from here. So this one can do a 2D traversal using the recursive algorithm. Is that okay?
Yeah.
We probably never see this before, but this one is also very important, okay? When you need to do recursion on 2D, I think it's a little bit more difficult, but still in the boundary of A becomes A can test, okay? Because it's 2D and it's recursive. But practically, I think that very likely they won't test something this difficult, okay? But you have to be prepared anyway. And then your top level is starting from 0, 0. So as you can see, recursion, if you have the index, usually it's a helper function. The main function, the regular function you will do is you call it that is, okay. And it is two number keep changing is okay. You just need to make sure that your termination condition have special ij combination. So if you have only one index, usually it's I less than equal, greater equals eta less. That is the termination condition. Right here actually is two-dimensional. So both there is actually a termination condition. Otherwise, your recursive call is on these two conditions. If not changing line, you continue to grow J. If changing line, you reset J and then start from next I. It's okay? When these two both doesn't happen, you will go to the termination condition. So it actually is fine. Any question on this one?
No.
No.
Okay, so it's not really that hard, okay? And then you have recursive paradigm, divide and conquer, and dynamic programming, okay? So divide and conquer means your problem, you will divide a problem into the smaller one, and then solve the smaller problem. So binary search is divide and conquer. You start from the middle, and then you go for this one or go for this one, just divide and then conquer. Solve the problem in the smaller problem, and later you combine it. So this one also for the merge sort is also divide and then divide. And solve the problem and then combine. Okay, that's divide and conquer. Next one is called dynamic programming. Dynamic programming is an optimization problem. We call it dynamic programming. So dynamic programming is for like Fibonacci code. You have f of 4 equals f of 3 plus f of 2. So your bigger problem that you use a smaller problem to solve it. That's called dynamic programming. Okay, that's called dynamic programming. So this one is different from the top down. Okay, this one is different from top down. So let's see. Actually talk about this Fibonacci one more time. Okay. So let's do public static integer people integer n. Okay. So regular recursion is n equals 0. Return 0. I'm sorry, return 1. I'm sorry, return 0. I'm sorry. If n equals 1, return 1. So these two are the two termination conditions. Okay. And then you return f of n minus 1 plus f of n minus 2. Okay, this one is the Fibonacci code regular one. Okay, now if we are doing the public static integer, we are doing the Fibonacci function, but this one is with index. So this one is called DP, dynamic programming version. Okay. You have Fibonacci of integer n. Okay. And then you have integer f1, integer f2. Okay. So these two numbers representing for f of n minus 1 and f of n minus 2. Okay. And then you should also have the longing index I. Okay. So if n equals I, okay, you return f1 plus F2. Okay? That say that if your f of n will be equal to f of n minus 1 plus f of n minus 2. Okay? Otherwise, you will return, okay, people dp dynamic programming n I plus 1 f1 plus f2 f1. This one given new f1 equals f2 equals f1. Okay? So here we write the regular call function. So this one actually is a helper function, okay? It is a helper function. So this one would return Fibonacci function of n, okay, and your index starting from 0, starting from 2. Okay, these two initial conditions still needed, okay? And then you write this, you start from 2. So f of 2, if n equals 2, then you directly return 1 plus 0. That's actually f of 2 equal f of 1 plus f of 0. So n equals 1, n equals 0, you already solved it, okay? So n equals 3, you call f 3, 2, 1, 0. So you come to here, you will call f of 3, 3, 1, 1. And then f3 is 1, 1 would actually return 2. Okay? Is that okay? Is that okay?
Yeah.
Okay. How come it didn't run? Oh, I'm sorry. This one is people DP. Okay. Any question? Okay, so here, this one, you will call f of 4, calling f of 3, calling f of 2, and f of 2, calling f of 1, calling f of 0. This one called f of 2, calling f of 1, this one calling f of 1, and calling f of 0. So this one actually is order of 2 to the power n, is exponential growth. Okay. Well, this one, you see, it actually f of, let's assume this is 4, okay? We're calling f of 2, 1, 0, you call f of 4, 3, and then 1 and 1, okay? These two sum together to here, okay? And then this one will call f of 4, 4, this two sum to here, that's 2, and this one come to here is 1, right? And it will be getting this one with totally 3. Okay, so here it just make 1, 2, 3 call. So this is the order of n only. Well, this one will become a tree, actually become a tree. So this one is more complicated. This one actually just order of n. So your order n apparently you're coming from 2, 3, 4, right? It actually just one dimension. It actually is order of n. Is that okay?
Yeah.
So this one is a bottom up. So when you write recursion, you have to know about it. Okay, you have to know about it. And when you solve the problem, it's also you need to know that if you look at the so-called multiple choice problem, this one it will be faster. Okay, this one will be faster. Okay, let's continue. That's called dynamic programming. Okay. You can also write the iterative function in the iterative way. Okay. You can also write the for while loop for it. Okay. There are two ways. Actually, dynamic programming, one way is to bottom up. That's called tabulation. Okay. And there's also another way called top-down dynamic programming is called memorization. Okay. Two different ways. Both okay. This just means that dynamic programming you can do f of 0 calling f of 1, getting to f of 1, f of 1 go to f of 2, go to f of 3, something like that. That's called tabulation. That's bottom up. And you can also do the other way around. You can also do f of 4, calling f of 3, calling f of 2. Okay, this is called top-down approach. Okay, top-down approach is called memorization. Bottom up called tabulation. Okay, anyway, this one is beyond AP level. Okay, this one is already data structure problem. Okay, tail recursion will improve the program performance. But the exam doesn't test you the tail recursion, okay? AP doesn't test you the tail recursion. We just mentioned about it, okay? Anyway, the recursion, the theory is not hard, but let's look at the problem set, okay? The theory itself is not really hard, just very simple guidelines. Okay, but the programming part would be harder. Okay. Okay, let's look at the problem. Let me also bring up the answer. Okay. Okay, this time let's actually get started from Benjamin. Benjamin number one. Which of the following statement is true about recursion? All right, Benjamin, are you there?
Um, I don't think two is right.
You
Two.
go one by one, okay?
Okay.
So one okay or not?
One is okay.
One is okay. Two.
No, two isn't. Cause it's yeah, cause it's okay. So tail recursion is like the last operation, I guess, or like the last thing you do in the function, but it's not a requirement for those algorithms, I don't think. And then three
Divide
should
or conquer, actually, you divide or conquer, you actually sometimes you have, you break down, right? Let's look at the merge sort. You break down, and then later you need to combine.
yeah.
Yeah. So when your data return from the smaller case, you still need to do combine. So this one is wrong, right?
Yeah.
You have a combine, and that's not tail recursion.
Yeah. And then number three, it's true. It's basically like the fundamental principle, I guess. So like
A process is defined in terms of simpler case of itself.
that is basically what a
That's
recursion is.
basic recursion is. So one and three,
One
you
and
pick
three
D.
is yeah.
Okay. Let me see. Problem two, let me have Elaine, problem two. So problem two, okay, still
Um,
one, two, three. Here is the one to n, so which one will sub the one to n? One okay or not?
uh, one not okay. So I think like it'll just keep going on. So it'd be overflow.
One is missing the if statement, is don't have the termination condition.
Mm. And then
Two,
two, I think it works.
it work, okay. Three,
And then three, since it like calls itself with the same input, I believe that it will go on forever. So it doesn't work either.
it doesn't work, yeah. And also you will explore. Even if you put n minus one, n minus two, still wrong. It is wrong algorithm, okay? So this one is two only, okay. Number three, let me have Maneni number three. How to analyze this problem? But anyway. The termination condition, you will stop, or you will not stop actually. This one you will not stop. So let's see, if the length is less than 15, if the length is below 15, you will print, right? You print. So, but let's get started from, let's assume that we actually starting from 0 character. So 0 character will go, what will happen to it if you starting from 0 character? But then it will happen if you start from 0 character.
Nothing will be printed.
No, you have to trace it. 0 character, you process star. So you start from 0 character to become 1 star. And then you call star star. And then, but then what will happen? What will happen? You keep growing, and then shoot. Right?
Yeah.
But from 0 to 15, there will be printing. So if a number starting from 7, say, if you were like A, B, C, D, E, F, G, same thing, it would be this, and then A, B, C, D, F, G plus a star, and then keep going, and then shoot to the roof. If you're starting from 16, A, B, C, D, whatever, and then you add in the star, and then go to the roof. So what should you pick? Which one will terminate without error?
B.
Wait, we already do the analysis. Why you pick B? Which one will terminate without error? Which one will terminate? No character, you will shoot to the loop, never stop. 7, you will shoot to the loop, no stop. 16, you will also shoot to the loop, never stop. So for no input, no string input, that will stop. It's actually E. We already did the analysis right here. So you see the recursion is very easy, just 3 lines of code, but when you analyze, you have to be careful. I do the diagram for you, okay? Melanie, is that okay?
Yeah.
You do the analysis. So sometimes some problem like this, you do analysis, maybe it's actually 0. You go from the big number down to 0 and it stop. Actually, it has a termination. Maybe it doesn't stop. You count down, but you never stop. Then that's actually no termination condition. Maybe you actually do this, but eventually come to here, that will stop. Okay, but you can do diagramming for it to determine whether it stopped or not. Elaine, is okay? Is it okay for this one? So how about number 4? Go back to Benjamin. What happened to this one?
Oh, when will it terminate without error?
Okay, let's try bigger than 15. What happened?
Then bigger than 15, then it just doesn't do anything.
So doesn't do means anything means what?
It just doesn't print anything.
Just means stop. You will stop right there.
Oh.
I don't do anything, just do stop. It actually has a hidden return over there.
Yeah, okay. So
Then you start it from 0. Let's assume that you got a string of no character. What happened?
be recursion s dot star, and then so it become yeah, s will become 1, and then 2, and then 3, and then 4, and then just keeps going until 15.
Right? And it stop. So you
Yeah.
want 1, what happened?
Then you would go to 2, and then all the way up to 15.
Okay, so which one would terminate without error?
B.
You read it carefully. Use the B. Over 15, you stop right away. Everything start from 0, 1 to 15. What happened? You stop all at 15. So essentially, this one is for all input strings,
Okay.
right?
Yeah. It's from name without error. Yeah. Yeah, that
Okay,
would be.
okay. You guys have to use your brain, okay? It's not hard. You have to trust your analysis by yourself and make the right reading, okay?
All right.
Right? Make sense?
Yeah.
Number 5. Let me go back to 11, number 5.
For 5, if you put in result 5, it would become 2 to the power of 5. So it'd be B32.
Okay? This one is top down, right? Now, if you do button up, recursive of 1, you got 2. Recursive of 2, you got 2 times 1. 2 times 2, you got 4. Recursive of 3, you got 4 times, I'm sorry, 2 times 4, you got 8. Recursive of 4, you got 2 times 8, you got 16. Recursive of 5, you got 2 times 16, got 32. So bottom up easier or top down easier for this problem?
Top down.
I would say this one easier. I would say this one easier. Why this one is easier? You have to look down from 5, 4, 3, 2, 1. It's not natural. This one apparently you actually get this one is 2 to the power 1. This is 2 to the power 2. You actually very easy to see here. Okay? Elaine, is that okay?
Yeah.
Why am I talking about this? Just because when you see a recursive function right here, you have to make a decision whether you go this way or you go this way to trace the problem. It's not just looking at the problem and then, wait, let me see what happened. You have to analyze it using the right tools, right way, okay? Manani, does that make sense?
Yeah.
Okay, so here, this one is the same as previous one, okay? So result n actually you getting what? How many times will result be called? It's not talking about the result itself, it's the how many times the result function will be called. So this one is your R5 calling R4, R4 calling R3, and then R2, and then well, this one had to do top down, okay, and R1 you return 2. So basically 1, 2, 3, 4, 5 code, okay. So actually it's N code. This one is not 2 to the power, this one is talking about it. Not talking about result, it's talking about how many code you need to do. Right? Is that okay? Number 7 for Benjamin. Number 7. This one actually is a accumulator and a number, growing number, that's indexing.
Isn't that just B?
Hmm?
Isn't that just B? So it goes to 3, and then 2, and then 1. Then it would be 6 plus 2, and then 6 plus 8.
So let's see, if the n equals 1, you return a,
Yeah.
right? So let's assume right here it actually is n equals 2. Then you will be calling m of 1 and a and d. That will return a, right?
Yeah.
So n equals 2 equals, so it's a and a plus b. Then this one's n equals 1, is n equals 2. And n equals 3, it is actually d plus n equals 2. So it actually a plus 2d. So n equals 4 should be a plus 3d. So what is this?
Oh, that would be 2.
No, I'm talking about what is this? How do you call this one?
That would be the second one, right? The D.
No, in math, what is this? How do you call this in math? This is actually A1
Plus-
equals A. A2 equals A plus D. A3 equals A plus 2D. Any one of you know what is this in math?
Is it arithmetic, right? Arithmetic sequence or something?
Yes, this is called arithmetic sequence. Wait, everyone just. This is simple math. It's called arithmetic sequence. Okay?
Yeah.
So right here, this is 3. 3 would be A3 should be A plus 2D.
So that would be 14. What? A is wait, Mr. Cho.
H2, I'm sorry, H2.
Yeah. So that'll be 14, which is B.
14, which is B. Okay? Why am I discussing this? Just because that I can just tell you to solve it by doing recursion. Okay, that's one way. But if this problem, this is not 3, if this one is 300, what will happen? You cannot do it, right? But if I know it's actually a arithmetic sequence, then A300 should be equal to A plus 299D. Solvable or not? Actually solvable, right? Does that make sense? Hello, does that make sense or not?
Yes.
So some of the recursive problem you cannot just solve by tracing it, top down or bottom up. Sometimes you need to know about the nature of the computing. If you discover this one is an arithmetic sequence, you can do it. So even 300, 3,000, I don't care. You can solve the problem. Okay? Number 8, let me have 11.
Because 6 is less than
So you read the
8.
problem, there are a lot of recursion, and then what will you do?
Sorry, could you repeat that?
You see this recursive function and you see two numbers, and then you start to have f of 6a, and then what will you do? You do looking at which case it is?
Yeah.
Yeah, and then you have
so
f
it
of
would,
k, and then 2.
yeah, so
And
it
then
would 2, and then it would
this is
be
the wrong
f
path.
of,
You
yeah.
use time. So you read this problem, what happened to this function? What is it doing?
If the first number,
So overall, what did this f function really do? Okay, previous one we see is an arithmetic sequence, but this one, what would be the result for every function?
the result is making,
Anyone know what the
it's
result should
making
be?
it's making both of the numbers equal.
No, it's not making the both number equal. It returns when
It's
they are equal.
returning it's returning the greatest common factor of both numbers,
Yeah,
right?
so this one is actually to relatively read is 2.
Okay.
This is second A. If it is actually f of 196 versus 144, what will happen? You will spend a lot of time doing it, right?
Yes.
So this one, you read it, you need to know about GCT. In GCT, do we cover it? Yes, we do cover this algorithm when we do the GCT. So when you solve the recursive problem, you do try to understand the nature of computing first. If you know about the purpose, that's it. You use the purpose to solve the problem. If you don't solve the problem knowing about the purpose, then you go down to trace the numbers. And then when you go down to trace the numbers, you have a bottom up and also top down to do. But this one, if you trace down, bottom up is impossible. So you have to go top down. And top down is a very painful way to do. Okay? So this one, if you know the problem it is a GCD algorithm, then you can solve it right away. If you don't, then you have to go to top-down approach to solve it. Then that's very painful. Okay? What I'm trying to emphasize is that recursion, first you need to know about the purpose. If you don't know about the purpose, you do need to know about the right way, up, down, or bottom up. Okay, that's the principle for doing recursion. Number nine for Manelli. So this one again, I'll let you work on it, okay? But anyway, I'll ask you a question. What is the purpose for this one? Not just knowing about I equals 1, I equals 2, I equals 3. Okay, I don't care about I equals how many. Tell me what's the purpose for this one. Can you read the purpose of this one or not? But then you hear me? I'll let you work on it, okay? But then you hear me? Hello? But then do you hear me? Oh, there's no response. Benjamin, can you tell me what's the purpose for this one?
It's um, so n equals 1, then so I guess, is it A? I'm not sure what this one is, to be honest. So
You have an array.
yeah,
Now this one is called n, right? You call n. So when you are actually, if you n down to 1, you will return this right away. Okay, that's
Yeah.
termination condition. So if you are n, you will calculate the n minus 1 case. So n minus 1 case means you're working on the previous one's result right here. And you will compare this one's result and this number. If this number is bigger, you will return this one. If not, you will return the previous one's result. So apparently, this one is finding the maximum. So it's finding a large number in x and x no change. So that's the purpose. Okay. Benjamin, is that okay?
Yeah.
About Benetti, you hear me or not?
Yeah.
Okay, I try to call you, okay? You have to answer, okay? So this one is actually, you have to know about the purpose first, okay? Otherwise, you will be wasting time. It's very hard for you to solve it. Okay, but then you repeat this one, okay? You work on this one. So same thing, you need to know about the purpose of this one. So what's the purpose of this one? But then let's talk about it in this way. What is the termination condition? When will this terminate? The program no longer recursive.
If the length of S is
Is what?
not greater than 0.
No, greater than 0. Yeah, not greater than 0. So what is not greater than 0? You have a string. What does it mean by not greater than 0? So that means that S is equal to empty string. Okay? So its communication condition is that you actually go down to 0. Empty string, then you will terminate. So how does this algorithm behave? Okay, now we don't care about the termination condition. It's greater than 0. So every time, what do you do? You have a string, and you do what? You print out the rest of the string. You print this part, and then you print single character. So you print single letter after your smaller case. So let's assume you have A, B, C. You should print B, C first, and then you print the A later. So this one you print a C first, and then you print B, and then you print. You actually print nothing, and then you print your C. So this one, in fact, you will be reverse order. So it's B. Okay?
Yep.
You have to really understand it, okay? You have to do it, not me to solve the problem. I'm actually just guiding you to solve the problem. Okay? Any question, anyone? So recursive function usually very easy, but you have to understand the purpose. No matter which one, you have to understand the purpose first. You don't understand the purpose, you cannot solve the problem. It look like easy, just 1, 2, 3, 3 lines of the code. Okay. Number 11, let me have Elaine.
So for this one,
This one, you have B and E. You actually try to calculate E raised to the power E, right?
yeah.
So 0, okay, greater than 0, okay, now you have the E less than 0. So what you should get is 1 over B's E absolute value, right?
Yes.
So which one it is?
I think A would work the best.
This one
'Cause
become more negative,
yeah,
right? E is negative.
yes.
This one become more negative, so it won't stop, right? So basically,
Yeah, so it
E
never
and
stops.
P, they are gone, they never stop. This one time the B, C is also down because you every time you time the B, that's also not good.
Yes.
So you have A and this, which one it is? This
I
one,
think it's
you no change, so you keep calling the same function.
yeah.
So this one done, it will never stop. So A is the solution. Okay? Okay? C and
Yeah.
D is done because every time they time a base, that's wrong. It's actually 1 over B. Okay? And then this one, it never stop because your exponent keep dropping down. This one, you never change your exponent. It's also done. Okay? So this one is A. I'm a little bit out of wrong order now. Let me have Benjamin answer.
Oh my goodness. N is greater than 0, so
So N0 what happened? 2 0 what happened?
D0 would be it just wouldn't print anything.
Right?
Yeah, it just wouldn't print anything.
B equals 1 what happened?
D0, 1, D0.
B equals 2 what happened?
D1, so it would be D1 and then 2 and then D1.
D3 what happened?
3. Okay, so okay.
This is a typical bottom-up problem. Don't go top-down. It'll be more difficult. Does that make sense?
Yeah.
So when you need to trace the program, you have to determine whether it's going top-down or bottom-up. How I know that this one bottom-up is better? Because you do little experiment, you can handle everything. You go top-down, you actually don't know what is N minus 1. You don't know. Then you go into a lot of tree structure that's more difficult. Okay?
Yeah.
Number 13, let me have 11. Number 13, 11.
So the okay, so I think that they want like they read the integers until it sees that
So what
-99.
this one is, if you use the English to say it, what would be the result that you get?
They have the even numbers in like reverse order from
Okay, so
like the original
okay,
list.
now you know it's actually get the even number but in reverse order.
Yeah.
So which one would do the reverse order and then the even number?
One, it would not work because it's in the original order.
Hmm. 2?
And then two, it doesn't work because it like only does the recursion when the number is even.
Hmm.
So the -999 won't work. So it's only 3.
Hmm. You should be careful, okay? It doesn't mean that you do recursive call on even number. The recursive call need to go for every number, okay?
Okay, yeah.
That's print only happen on the even number. But print need to be after the recursive call. We'll give you the reverse order. Number 14, Maneni, your call. This one a little bit like Fibonacci, okay? So Maneni, how to solve this problem? Hi, Maneni, are you okay? Hi, Maneni, you hear me?
Yeah.
So how do you do this one? So it didn't tell you everything less than 0 is 2, so you can write n minus 2 equals 2, n minus 1 equals 2. How about m0? So n minus 3 also equals 2. So m0 is what? What is m0? And Benedict, what is m0? Hello? M0 is what?
Oh, -1 plus -3.
So what is the result? I
4.
already list down here. Is 2 plus 2 equals 4. How about m equals 1? m1.
6.
Okay? Is that okay?
Yeah.
It's still a bottom-up problem, okay? Number 15. Number 15, let me have Xavier. Xavier, how are you? So how do you do this one? 15, T5, what would be T5? Xavier, you hear me?
Yeah.
So how to solve this problem?
You just you just plug it in. So I got
How to solve it?
-4.
No, step by step. What do you get started?
But
Do
so
step by
n is
step.
equal to 5. So then, since n is not 1 or 2, then you do the else statement, which is t of 4 minus t of 3. And then
About T of 4.
that's t of 3 minus t of 2.
About T3.
T of 2 minus t of 1.
Hmm?
T of 2 minus t of 1.
T of 3.
T of 2 minus t of 1.
So what is the result?
That's 2.
So this one is 2 times 2. This is 4 minus 2. This is 4 minus 2. So this one is actually 2. So this is 2 minus 4. This one is negative 2. So this one is negative 2 minus 2. Actually, you got minus 4. But this way actually is a more painful way to do. Okay, let's keep it this one. So totally how many core you need to have? You actually have 1, 2, 3, 4, 5, 6, 7, 8, 9 core. Okay. This one totally 9 core. But if you do bottom up, you will see T of 1 equals 1, T of 2 equals, T of 1 equals 2, 4, T of 3 equals T of 1 equals 2, T of 2 equals 4, T of 3 equal T of 2 minus T of 1, 2. T of 4 equals minus T of 5 equals minus 4. So still bottom up is better. Okay? Still bottom up is a better solution. So T of 6, how many core you have? This one you don't care about the plus minus, so you just put T of 6, 5, and 4, minus doesn't matter. Okay, you just calculate how many core you have. So you can do top down, you end up with 1 core, 2 core plus this one. So F3 equals 3 core, 2, 1 core. So this one is 1 plus 1 is 3, 1 3 plus 1. This one actually 1 3 plus 1 actually this one is 5 core. So 5 core right here. This one is 3 core. So this one is 9 core. This one plus this actually this one is 15 core. Okay. But you can also do bottom up, 1 core, 1 core, 3 core, 5 core, 9 core. fitting code. Okay, this still be easier if you go bottom up. Is that okay?
Yeah.
17, let me have Benjamin 17. This one is F1 function calling F2 function. F2 function also calling F1 function. This in theory, we call it coroutine. So when coroutine happens, there's no way to analyze it scientifically, like knowing about the purpose. So this one you can only go for putting the number in, plugging the number to test it. Okay?
Okay.
There's no way that you figure out what is going on, what is coroutine, because you have function one calling function two, but function two may also call function one. So you can only go step by step. So let's look at it. You do have F1 of phi 3. So what will happen F1 to phi 3?
We'll go to 5 plus F243.
So F243 will happen.
That will become 4 plus F123.
So what happened to F123?
That 2 plus F213.
What happened to the
And it would just
F2
return, and then it would just return 4.
return 4? So you can return 4. So that's
6, 4, 5, so that's 15. That would be,
2 plus 4, right?
yeah.
2
That would be
plus 4, that would be 6.
6 plus 4 is 10. 10 plus
10.
15, which is E.
So you got E. Okay, this one actually no better solution because you cannot understand what's going on. No, if you try to understand the purpose, you will not get it. Okay, impossible to know the purpose. So in this case, you have to do brute force checking. Okay.
Yeah.
Number 18, let me have Elaine. How to do this one? Right?
Yes.
So what's going on?
They're doing a factorial, but it depends on like the x value.
So this one is not factorial.
Yeah, so
This one is not. This one is also. This one both are, but this one is not. So what is the summary?
the summary is that if it's x equals 3, then it does not do the factorial, but otherwise it does.
So it actually is. Right?
Yes.
So F3 is actually 3. F4 is what?
F4 is 4 times, or it's 12. Yeah, sorry.
So you got 415.
So yeah, so it'd be A.
Okay. This one's still a bottom-up problem. You go top down, you are in big trouble. Okay. Number 19 for magnetic number 19. So what does this right 3-digit do? Let's assume you get a number 456. What will happen? Hi, Vanity, what will happen?
It'll print 4 and then 5 and then 6.
So it print 3-digit by itself. What about if you get 21? What will happen to 21?
0, 2, 1.
Okay, so you keep a number that will print like this. Or if you just get 7, you actually print 007, right? So every 3-digit, this one basically just print every 3-digit. How about this one? This one right with comma. What happened to this right with comma? So that's when you have 1, 2, 3, 4, 5, 6. What happened?
It'll print 1, 2, 3, comma 4, 5, 6.
No. You write this first. So it's 4, 5, 6, comma 1, 2, 3. Okay. So if this 1, 2, 3, 4, 5, 6, and then 7, 8, 9, you do 7, 8, 9, 4, 5, 6, 1, 2, 3. So what is the function of this right comma? Right with comma. I believe what is the purpose of this right with comma by the function? You print out 3-digit with comma in reverse order, right?
Yeah.
So which one will not be printed correctly? It won't be pre-printed with comma, but it actually the function that you do is actually in reverse order. So which one will create trouble?
C.
This one will create trouble because it's not symmetric. You become 0, 5, 1, 3, 6, 5. But you really won't, if it actually is symmetric, then it's okay. 3-digit symmetry, you'll be okay. So if you need to modify the program, which one would work? right? If you multiply, actually you change this with this, that would be in order. Okay? Is that okay? Is that okay?
Yeah.
Twenty-one is a geometry. This one actually too difficult, okay? But you need to trace it one by one, okay? And draw the diagram. So this one actually will spend some time. I don't think this one will happen on the exam. So this one you just study it. It actually is a B, okay? This one is a B. Eventually you will get this one. If you try to understand the purpose, it's very difficult to understand as well. And there's no clue that what this one really trying to do. Okay, so this one you just do step by step, put in the number there to figure out what's going on. Okay, with the number right here. So this one, I didn't find any better way to do it. Okay, it's just plug in the number and try to draw anything you got, whatever. So this one is says B. Okay. Okay, anyway, the recursion, the theory, I think is easy, but when you go to the problem, it's actually a little bit harder. Okay. Today we try to cover different kind of problem style and hope you get the idea. Okay. Okay. Any questions so far?
No.
For JB, you drop signal for a while. You must watch the video again. Okay.
Yeah.
Okay. See you next time. Bye bye.
Bye,
Thank you.
thank you.
Bye bye.
Bye.